Okay, so what this is showing is that what is the meaning of stability and how we can sort of visualize it using equal area criterion. But that we really cannot apply when we have thousands of generators. So what is done is that we have a set of electrodynamic differential equations which then give us the angle, and knowing this angle, and this angle is changing very slowly, so given that angle, we then do the phasor calculation on the whole system and find what the electrical powers are, which are then fed back. And the mechanical powers are coming in from here. So this is the way in which we can solve a very large system with thousands of generators and do this in a reasonable amount of time. And it is shown by means of a simple three-bus example like this, where a three-phase fault occurs on one of the lines. And the same principle or the idea is applied, where the electrodynamic equations are differential equations, whereas the power flow is determined by phasor equations, which calculates the power based on the rotor angles that are supplied by the electrodynamic equations here. And it shows the oscillation of two machines in the system, machine 1, delta 1 over here, machine 2, delta 2 over here, the oscillations of these two rotor angles, and it clearly shows that in spite of this fault, which is then cleared within the specified time, these two machines do not go out of synchronism. They oscillate with respect to each other, but these oscillations do not grow uncontrollably. That means the system is stable. Right. Now, coming to this dynamic stability, this is an example of growing power oscillations in this western U.S.-Canada system, which occurred way back in 1996, but there have been several cases reported like this. This is given in reference 4, it's taken from reference 4. And this is a case of dynamic instability. And this is caused by inadequate damping in the system. And this inadequate damping could be the result of fast-acting feedback control systems in generator exciters, in excitation systems. HVDC control can act very fast, and if they are not designed properly, they can lead to poor damping. And also these FACTS devices that are being used, again, they can contribute to inadequate damping. So there is a solution for that, and that is to design these power system stabilizers with care, and also HVDC control can be properly designed to give adequate damping. But the analysis of dynamic stability requires modal analysis, eigenvalue analysis, and that is beyond the scope of this first course. So here we will just introduce this phenomena, but we will not go to analyze it. Okay. So that brings us to the end of this module, where we have described what is meant by transient stability and why it's important, what is the principle behind it, why the system can become unstable, and how we can sort of visualize it or understand it by means of this equal area criterion, what is meant by critical clearing time. If you wait too long for this fault to be cleared and the transmission line to be, faulted line to be taken out, then the system can become unstable. So that's the critical clearing time that we can calculate using this equal area criterion. And then we saw this mechanism for calculating transient stability in very large systems, where we have electrodynamic equations as differential equations, and then the power is being calculated by means of equations which are in phasor domain, phasor equations. And then we also saw the meaning of dynamic stability. So thank you very much.